Electric potential and capacitance. Potential energy. System of two charges. If Q1 and Q2 are two charges separated by distance r, then potential energy will be given by Q1 Q2 divided by 4 pi epsilon naught r. Potential energy for system of three charges. Suppose there are three charges Q1, Q2, Q3, and suppose this separation is R12, this separation is R23, this separation is R13. Then potential energy of the system denoted as U will be equal to Q1 Q2 divided by 4 pi epsilon naught, separation between the two charges, that is R12, plus Q2 Q3 divided by 4 pi epsilon naught R23 plus Q1 Q3 divided by 4 pi epsilon naught R13. Now, potential energy of system of four charges. Suppose four charges are there, Q1, Q2, Q3, Q4. So potential energy in this case will be, let's write 1 upon 4 pi epsilon naught outside. Then Q1, Q2 divided by R12 is the separation between the two charges. Then next interaction Q2, Q3 divided by R23. Then Q4, Q3, Q4 divided by R34, interaction between these two. Then Q1, Q4 divided by R14. Then other possible interactions, 1, 3. So Q1, Q3 divided by R13. Then from Q2 to Q4, this interaction. So it will be Q2, Q4 divided by R24. So this is potential energy of system of four charges. Similarly, we can evaluate the potential energy for system of five charges. Okay, potential energy due to a single charge. So if potential in that region is V, then potential energy will be Q times V. Now, system of two charges placed in an external field, and then we have to find out potential energy. So suppose this is source charge, which is creating the potential. So suppose at this point potential is V1, and at this point potential is V2, and separation, this separation is suppose R12. Now we bring one charge Q1 at this point, then Q2 charge at this point. So now we have to find out what is potential energy of this system. It will be, as we know, that potential energy equal to Q times V. So when Q1 charge is brought at potential V1, then potential energy at this point will become Q1 times V1. Similarly, for this, when Q2 charge is brought at potential V2, then potential energy will be Q2 times V2. Now, we have to consider the interaction between these two charges also. So Q1, Q2 divided by 4 pi epsilon naught, and separation between these two charges, that is R12. So this is potential energy of system of two charges placed in an external electric field. Now, let's see potential energy of a dipole in uniform electric field. So suppose this is uniform electric field and a dipole is placed here with the positive charge and negative charge here. In this direction, force will be, direction of electric field is this. So in this direction, force will be QE, and in this direction, force will be minus QE. And suppose we draw perpendicular, so we give the name to this point A, this point B, this point C. So this will be perpendicular distance, and the length of dipole is 2A. So AB we can find. So AB upon AC will be sine theta, and AB is to be found. So AB equal to, and AC is 2A, so 2A sine theta. Now net force will be QE in this direction minus QE in this direction, so that will be 0, and the torque, which is force into perpendicular distance, force is QE, and perpendicular distance is 2A sine theta, which is equal to PE sine theta. This is torque. Now we have to find out the work done in rotating this dipole through an angle theta, but we will consider the dipole to be at 90° to the external electric field, and then we will try to rotate it through angle theta. So first, let's rotate it through angle d theta, then small work done dw will be integration PE sine theta d theta y. Logic is very simple. Tau d theta will be dw. Similar to F dx, force into displacement equal to small work done. So in rotational motion, torque times angle moved gives the work done. So P sine theta d theta. So here we should not write integration when we have to find out total work. In that case, we will write integration. Now we write total work and then we put the limits. So as I told you, we assume that dipole is at 90° and now we have to rotate it through angle theta. So PE sine theta d theta. Integration of sine theta gives minus cos theta. So we will get W equal to minus PE cos theta and limits pi by 2 to theta. So this will give minus PE and cos theta minus cos pi by 2. And we know that cos pi by 2 is 0. So we will get work done, which is equal to potential energy, which is equal to minus PE cos theta. In vector form, we can say it is P dot E, because if you remember, A dot B gives AB cos theta. So this is expression of potential energy due to a dipole placed in external field. Now let's go to next concept. Capacitance of a spherical conductor. If you are given a spherical conductor of radius r and it is given charge q, so potential due to this charge V equals q divided by 4 pi epsilon naught r, and we know that q equal to cv, or q is proportional to v, and then we put one constant that is called capacitance. So from here we can put the value of q. So v will be equal to cv divided by 4 pi epsilon naught r. So we will cancel out, and we will get C equal to 4 pi epsilon naught R, which is required. Now, capacitance of a parallel plate capacitor. So we consider a parallel plate capacitor. So this plate is positively charged. This plate is negatively charged. Separation between two plates is D, and area of each plate is A. Now charge density, if we write, so this will be plus sigma, this will be minus sigma. Now, as we have already discussed, there are three regions, and we find electric field. So here, if we calculate, we will find that electric field in region 1 and 3 will be 0. So only it will exist between the two plates. So let's consider the second region. So electric field in second region, E will be equal to sigma upon epsilon naught minus, and this will become, it will change its sign, so this will become plus sigma upon epsilon naught. This is twice, because due to single plate, electric field is sigma upon 2 epsilon naught. So we will get sigma upon epsilon naught. So in this region, electric field is sigma upon epsilon naught. And we know that electric field is related to potential as E equal to V upon D. Here is separation. So we can write it E as Q upon epsilon naught, and here we are putting the value of E. So either we write here, so it will be better to write as V upon D equal to sigma upon epsilon naught, and sigma equal to charge Q divided by area. So V upon D equal to Q upon epsilon naught A, but Q equal to CV. So we put this value here. So we get V divided by D equal to CV divided by epsilon naught A. V will cancel out, and we will get C equal to epsilon naught A upon D, which is required expression. Let's recall it. So as you know that electric field due to charged plate is given by sigma upon 2 epsilon naught. So due to this positive charge in this region, it will be negative. Due to this negatively charged plate in this region, electric field will be positive, hence they will get cancelled out. In third region, the same will happen. Due to this, it will be positive. Due to this, it will be negative, so they will cancel out. In this region, they will add up. So we have got E equal to sigma upon 2 epsilon naught plus sigma upon 2 epsilon naught, that is sigma upon epsilon naught, and we know the relation E equal to V upon D. So we write in place of E as V upon D, so that will be equal to sigma upon epsilon naught, and sigma is surface charge density, which is charge divided by area. So we write this value here. So it will be V upon D equal to Q upon epsilon naught A, but Q equal to CV. So we put this value, and hence we have found C equal to epsilon naught A upon D. Now, capacitance of a parallel plate capacitor when dielectric is inserted between the plates. This is very important case for exam, so you must understand it properly. Suppose these are two plates. This is positively charged, having surface charge density sigma, and this is negatively charged, having surface charge density minus sigma. Now, between these two plates, we insert a dielectric having same area but thickness will be T, and this total separation is D. External field E0 will be in this direction. Induced field inside will be just opposite. On this face, positive charge will appear due to these negative charge. Induction will be there, and similarly here minus charges will be there. So we can say induced electric field EP will be in this direction. Direction is like this. So external electric field will be stronger than the induced field. So net field inside the dielectric will be E0 upon K, which is as E0. So it is difference of the external field minus induced field. So let's write it as E0 upon K. Now we can say that in a region D minus T, electric field is 0. So in region D minus T, field is E0, whereas in region T, field is E0 upon K. Now we are going to apply the concept of potential difference. So we know that V equal to E into R. Now V equals E0, and distance in which E0 is extended is D minus T, plus E0 upon K, and distance is T. Now we can take out E0, then D minus T plus T upon K will be left. Now we know that electric field E0 is equal to Q upon epsilon naught A. Why? Reason is very simple. E0 equal to Q upon 4 pi epsilon naught A. A is R square, and we write 4 pi R square as area. So that is why Q upon epsilon naught A. R, we can say that E equal to sigma upon epsilon naught, where sigma will be Q upon A. So we put this value here. So V equals, in place of E0, we write Q upon epsilon naught A times D minus T plus T upon K, and Q equal to CV. So V equal to CV divided by epsilon naught A times D minus T plus T upon K. So we will cancel out, and our concern is to get C. This implies C equal to epsilon naught A divided by D minus T plus T upon K. So which is our required expression? So we have got capacitance when space between the two plates is partially filled by a dielectric. Here width of dielectric is T, and the total separation between the two plates is D. So I think you must have understood. Now let's consider next concept, energy stored in a capacitor. So these are two plates of capacitor. Charge density plus sigma minus sigma. So here we are not going to write that thing. So we assume that initially charge Q is given to this plate, then due to induction minus Q charge will be induced on the second plate. Let's call these plates as A and B. Now potential due to discharge from formula Q equal to CV it will be V equal to Q upon C. Suppose we want to give further charge dq to this plate. This is positively charged plate, and if charge dq positive is to be given, then there will be force of repulsion. So against that repulsion, work is to be done, and that work is stored in form of potential energy. So work done, we know that work divided by charge equal to potential. So from that concept, we can say small work done dW equals V times dq. So total work done will be equal to, as I told you, it will be potential energy, which can be written as U, equal to integration V equal to Q upon C, Q upon C dq, and suppose initial charge is 0 and final charge is capital Q. So as you know, integration x dx gives x square upon 2. So from here we will get q square upon 2c limits 0 to q. So this small q will change to capital Q. So we will get q square upon 2c. So potential energy, that is U, will be 1 by 2 q square upon c. We can use q equal to cv to get another formula, and that would be half cv square. So potential energy PE will be half cv square. Now let's consider next concept, energy density. Energy density means potential energy per unit volume. So we know that potential energy of a capacitor is half q squared by c that we have just derived. Now we write q in terms of electric field. So we know that E equal to q upon epsilon naught A. So q will be equal to E times epsilon naught A. So we put this value here. So U equal to half then E square epsilon naught square A square divided by C, and C equal to epsilon naught A upon D for parallel take capacitor. So we put this value here. So epsilon naught A and divided by D can be written in numerator. So we have got 1 by 2 E square, and 1 epsilon naught will cancel out. So epsilon naught 1 A will also cancel out. So we will be left with A into D. And we know volume equal to area into separation in case of parallel plate capacitor. So area of the plates and the separation between the two will give volume. So here this is volume. So we can say potential energy divided by this can be written as volume. So this will become potential energy per unit volume, and that is written as energy density denoted as small ue equal to, so 1 by 2 epsilon naught E square. So this is our expression. Now let's see next concept, loss of energy in a redistribution of charges. So if there are two capacitances of capacitance C1 and C2, and their potentials are V1 and V2, then we can find common potential. So common potential V is given by C1 V1 plus C2 V2 divided by C1 plus C2. Now let's consider their energies. So initial energy Ui will be half C1 V1 square plus half C2 V2 square. When they are connected in parallel, then they will have common potential. So in that case, final energy U final will be half C1 V square plus half C2 V square or we can write it as 1 by 2 C1 plus C2 times V square, and V is equal to this much. So C1 V1 plus C2 V2 divided by C1 plus C2 whole square. Now we have to check whether there is energy loss or not. So for this, we find the difference of Ui and Uf. If it is positive, then we say that energy loss has taken place. So Ui minus Uf. So Ui is this much 1 by 2 C1 V1 square plus 1 by 2 C2 V2 square minus 1 by 2 C1 plus C2 times C1 V1 square plus C2 V2 square, sorry, C1 V1 not square, C2 V2 whole square divided by C1 plus C2 whole square. So 1 C1 plus C2 will cancel out, and we will get this thing. In denominator, only C1 plus C2. Now, if we take LCM, so what do we get? We will get 1 by 2 is common, and C1 plus C2. And then this C1 plus C2 will get multiplied to this term, and difference of these. So let's see. So it will become C1, when this C1 gets multiplied to C1, C1 square V1 square plus C1 C2 V1 square plus, in this term it will become C1 C2 V2 square plus C2 square V2 square minus, from here it will become C1 square V1 square, C1 square V1 square, and this will become C2 square V2 square minus twice of C1 C2 V1 V2. Here we have applied formula A plus B whole square. So, and because of this minus sign, these are written as minus. Now, this C1 V1 square, C1 V1 square will cancel out. Similarly, C2 V2 square and C2 V2 square will cancel out. Now we are left with C1 C2 V1 square plus C1 C2 V2 square minus twice of C1 C2 V1 V2. So from here we can take common C1 C2. So we are going to write it as Ui minus Uf equal to C1 C2 divided by twice of C1 plus C2. Then we will be left with V1 square plus V2 square minus twice of V1 V2, which is equal to C1 C2 divided by twice of C1 plus C2 times V1 minus V2 whole square. And here C1 C2 are always positive, and square of difference of two numbers is always positive. Hence, this is greater than 0, which means there is energy loss, and this loss occurs in form of heat and electromagnetic radiations. Thank you for watching.